Till now, we focused on the theory part. I'm sure you gained good fundamental understanding of MLOps. Now let's take things to the next level. So using a Hello World project, let's try to understand how MLOps engineers help data scientists and ML engineers in real time. Let's first understand the business requirement. Imagine an organization planning to build a system to predict flower species by taking petal length, petal width, sepal length, and sepal width as inputs. Now, for this business requirement, we will first see how data scientists tackle the business requirement, what activities do they perform. Then we will see how MLOps engineers helps the data scientists. After that, we will understand how ML engineers take this model to the next level. And finally, we will see how MLOps engineers help ML engineers. So the next few lectures will focus on this particular things. In this lecture, let's understand how data scientists tackle this business requirement. Of course, as a prerequisite, data scientists get in touch with the product owner or someone who defines this requirement so that the requirement is very clear to them. Once it is clear, data scientists start with step 1, that is data gathering or data collection. In step 2, data scientists work on setting up the Python environment. It can be installing Python or setting up Python virtual environment. In step 3, data scientists will actually start with writing the Python script. For example, that would involve loading the data set, splitting the data into training data and test data, and then choosing an algorithm according to the business requirement. This is very important. And once they find the algorithm, they use the algorithm in the script to train algorithm on the training data. Once this is done, once the model is available, data scientists work on saving the model. So these are steps they follow for this business requirement. Let's try to see these things practically as well. Basically, for this requirement, data scientists don't have to prepare a data set because there is a publicly available data set called Iris dataset. All that data scientists have to do is to import the data set and start using the data set. That's what we learned in the theory part as well. Sometimes data scientists might have to prepare a data set using internal or external data sources, but sometimes they can find the data sources on internet, especially if the use case is popular or very, very simple. In this case, Iris dataset exactly meets the requirements. As MLOps engineers, you don't have to understand how data scientists prepare a dataset, but still, I will quickly show you how Iris dataset looks like in real time. We will use the Python inline commands to read the Iris dataset. I'll use Python 3.12 and I've tested the entire project on Python 3.12. So make sure you also use the same version if you are planning to execute the project. All it takes is just 5 inline commands. First one is to import the dataset. Then we'll also import pandas because I'll use pandas for visualization. Starting with loading the dataset. Okay, so we imported the dataset here. We will load the dataset and then we will put the dataset into Panda data frames. We'll also use the Iris target and finally I will just print the data frame. Instead of printing all the lines in the dataset, which is usually huge, I'll just print first few lines of the dataset. So this is how it looks like. These are the input features and this is the output target. What does this dataset actually say? If sepal length is 5.1, if sepal length is 3.5, if petal length is 1.4 and petal width is 0.2, then the target is 0. But Abhishek, target has to be flower species. Why is target represented in a numerical format? It's okay, I'll just print the target names for you. You will easily understand it. So these are the target names: Setosa, versicolor, and virginica. So this is in a list, and 0 here represents the 0th index of the element, which is Setosa. If the target is 1, it would be versicolor. If the target is 2, then it is virginica. So usually this is how data is represented in a data set. Now that you understood the data set, let's go ahead and see how data scientist writes a Python script to train the algorithm on the data set. I already have the file here, train.py. Because you don't have to write the script, I'll not emphasize on writing the script, but I'll quickly explain you the script. Just like any other Python script, this will start with import statements, all the things that we use within the script, all the modules, libraries, and the packages. The first line here is basically to load the dataset, the dataset that we are going to use. And where did this come from? This came from the import statement. And these two lines here, these two lines play critical role in the script. This is basically for training testing split. We learned during the theory part, the same dataset is used for training and testing, but X percentage of the dataset is used for training, Y percentage of the dataset is used for testing. And this parameter here explains that 20% of the data will be used for the testing purpose. And then here data scientists choose the algorithm for the training process. This is the most critical step because here data scientist can also go with random forest or any other algorithm, but data scientist feels for the current requirement, logistic regression is the perfect algorithm. And this algorithm will be trained on the training data. It starts identifying the patterns and it will develop a mathematical function, which is basically this model. So model is the output of the training process. Now, once the model is created, rest of the files in script are pretty basic. So these lines here is basically for saving the model in the artifacts folder in the PKL format. And these lines here is basically for creating a metric file that is used for tracking the performance and efficiency of the model. If you don't want to create a metric file, you can also print the accuracy of the model onto the terminal. So this is how data scientists write the Python script. We'll quickly execute it. But before that, we have to download the dependencies. So we have used all the import statements here. We have to download these dependencies. Only then we can execute the script. For that, I also prepared the requirements.txt. So we can execute the requirements.txt. One suggestion here, whenever you are working with Python, it can be for machine learning, it can be for DevOps or any other activities, make sure you create a Python virtual environment. So I'll start with doing that. Python 3.12 -m venv followed by name of the virtual environment. And then we'll activate the virtual environment using source.venv bin activate. You can quickly verify if the virtual environment is activated by just running which Python 3.12. So if you see .venv here, that means virtual environment is activated. Perfect. Now, all that I have to do is Python 3.12 -m pip install -r requirements.txt. So this will download all the dependencies into the virtual environment. Now, once this is done, I will go ahead and execute the train.py to see the efficiency of our model. Python 3.12 train.py. Now, this is a very, very simple requirement, and data set is also almost accurate. So that's why you will see the efficiency of the model as almost 100%. But let me tell you, seeing the efficiency model with 100% is very, very rare, because the real-time use cases are complicated and you might not find accurate training information as well. As I told you, in this case, test accuracy is 100 and model is saved to artifacts model.pkl. So if I see the artifacts folder, you should find that model.pkl. But Abhishek, how data scientists execute the model? Let's say they want to evaluate the model with test data. How do they do that? For that, they again write a script. Run underscore model.py is the one that I took as example here. And this is usually very, very simple. All that they have to do is to invoke the model with example parameters. In this case, input features. Let me show you. So this is how they do it. Python 3, run model.py, -- input, followed by input features. So let's say I'll pass some random features. 10, 1, let me give spaces, 5, 10. Okay, what does it say? Prediction is 2. Let's say if I just change one of the parameter here and I'll just change this to 2. Now it says prediction is 1, which is versicolor. If I just go with, let's say 1, 1, 1, 1, then it says prediction as 0. So this way it predicts the output depending upon the input parameters. So this is the typical day-to-day flow of data scientist. This is a very, very simple example, but still you might have noticed a lot of manual activities. It can be having the script on the local machine. It can be executing these commands manually. Every time data scientist makes changes, they have to run all of these commands manually. And if they move to a different computer, again, they have to set up the Python virtual environment. They have to download the dependencies. They have to copy the files. They have to execute these commands. Let's see how MLOps Engineer helps data scientists. We will see that in the next lecture. Let's understand how MLOps Engineer helps data scientist team by automating these manual activities. But before that, what are these manual activities? Number one, imagine there are two data scientists in a team, A and B. A makes a very, very simple change to train.py and A wants to get it reviewed by B. In this case, B has to set up the complete environment locally, including setting up Python virtual environment, installing dependencies, getting the latest changes of the file, running the unit test cases, running the end-to-end test cases, and finally executing the train.py and verifying if the changes are fine. On top of that, imagine if this model is compatible with 3 versions of Python, or all the 3 versions of Python are supported. In this case, the work of B becomes even more complex, because instead of setting things in the local environment, B has to set up 3 virtual machines, each virtual machine with a version of Python. And for the specific version, B has to figure out how to install the dependencies, how to set up the Python virtual environment, and finally run the train.py and verify the changes. So you can understand how complex are these manual activities. And all of this for simple hello world model. Let's say if these data scientists are dealing with enterprise model, these steps only go high. So the number of steps increases, number of manual activity steps also increases. MLOps engineers can greatly help in this case. How? Let me explain. First things MLOps engineers can do is to introduce a version control system. Now, introducing version control system is not at all a big deal, but along with introducing version control system, MLOps engineers can also introduce best practices like branching strategy, one branch for one environment. Along with that, RBAC to ensure only right people make the change, and also introducing things like auditing. Along with that, MLOps engineers can also introduce CI/CD in the version control system so that CI/CD takes care of testing. It can be 3 Python versions, 5 Python versions, or even 10 Python versions. CI/CD can automate everything along with setting up Python, installing the dependencies, running the train.py, and printing the efficiency of the model. If required, saving the model along with the performance to a common location. Everything can be done by CI/CD that is introduced by MLOps engineers. Now let's try to see these things in action. So as MLOps engineers, we will start with creating a repository, and within the repository, we will push the files and we will set up the CI/CD. So let's use the default organization. If you're working in an organization, you should choose the organization's GitHub organization and provide the name of the repository. In this case, let's just call it Hello World MLOps. For now, I will choose all the options default, but by the time you see this repository, the repository will be completely updated with README file and all the details. Now the next step is to push the changes to this repository. So we have all the files on the terminal. We saw all the files. It is always a good practice to avoid pushing files like .venv. I mean the folders like .venv, which has all the dependency related information. So again, this should be taken care by MLOps engineers to introduce best practices like .gitignore. So I will add .gitignore and I will add .venv. Perfect. Now let's follow the steps provided here. Let's initiate the Git repository locally. Let's add all the files instead of just the README file because we have multiple files here. I have added all of them. If I just do git status, you can find all the files. So we'll also commit these files. I'll just call it as first commit and use the main branch. Add this remote repository, right? And then let's push these files. Perfect. So now we should have all the files in the remote repository. If I just refresh it, there you go. All the files are here. Now the next step is to set up CI/CD for these files. How will we do it? We will use GitHub Actions. This is actually even more simple, especially if you're coming from DevOps or cloud background, because you already know how to set up CI/CD for traditional applications. The steps are almost the same. So we will first start with setting up the CI file. You can either pull this code to your Visual Studio Code or any IDE, or you can also just click on the dot so that you can open Web IDE provided by GitHub. This is a single file change, so you can also do that. So I'll start with creating a folder, .github, and within the .github folder, I'll create another folder with name workflows. So within this workflows folder, we will create a file called ci.yaml. To be honest, you can change the name of the file. That's totally up to you. But what you write within the file is even more important. Once again, what are we going to write within this file? We will define GitHub workflows in a way whenever someone makes change to the train.py, model.py, or any file within the repository, this workflow should execute and it should train the model and save the new version of the model within the file. Because we are dealing with GitHub workflows, a new version of the model should be uploaded as an artifact so that someone else can go to the GitHub workflows and download the new version of the model. Let's see how to do it. So again, just like traditional applications, we will start with providing name to the CI file. So I'll just call it CI to train and save the model. Perfect. Now, whenever you write GitHub workflows, it is important to define action on which the workflow has to trigger. So here there are two major options. One is push action and other is pull request action. I'll use both of them. Okay, so this workflow should trigger when someone commits to the repo or when someone creates a pull request to the repo, but not to all branches. I'm only interested in main branch. So I'll just say main. Same thing, copy and paste it here. Perfect. So now we defined action on which the workflow should trigger. Now that we have the action, next step is to write the jobs. This is the main part of GitHub workflows. You define a job. Within the job, you define the steps that you want to run. In this case, the steps are to install Python, install the dependencies for the project, and then train the model, finally save the model. Okay, so let's provide name for the job. You can have one job or multiple jobs. In this case, we just need one single job. So we want to run multiple versions of Python, right? Same model, we want to train on multiple versions of Python. So I will be using the matrix. That's why I will call the job name as matrix pip. You can also change it. Again, it's totally up to you. Let's also provide a description to it. Okay, so I'll just say test, or I'll use the same description, train and save the model. Cool. Now, GitHub Actions needs a runner. Either you have to provide the runner or you can use the GitHub self-hosted runner. So I'll use a GitHub runner. So runs on Ubuntu latest. That means this workflow will use the GitHub runner. Because this is a public project, it is absolutely free of cost. How do you run the same job on multiple Python versions? This is where you use the strategy called matrix strategy. Okay, so that's why I named the job name as matrix pip. If you want, you can also call it as Abhishek. It doesn't matter. So within the matrix, we will just define Python and we will define the versions of Python on which you want to execute the job. 3.11, 3.12. Let's say on both of these Python versions. If you want 10 Python versions tomorrow, all that you have to do is just increase the version numbers and your CI file will run on 10 different Python versions. That's the beauty of CI/CD, right? Automation to the core. Now we will start with defining the steps. You should be able to guess the steps. We have the virtual machine. We have the actions on which the workflow has to trigger. So what will be the steps? If you followed the lectures carefully, whatever steps that we executed manually, we will put the same steps in GitHub Actions as well. First step. Okay, give it a guess. What should be the first step? The first step should be checkout. So check out the source code so that the virtual machine has the required files. GitHub Actions have a lot of actions which can automate the code for you. So instead of writing a shell script to pull the code from the repository, you can use an action called actions checkout. The latest version, I believe, is V5, but let's use much stable one, that is V4. At least I have tested the code with V4, so I'm using it. Then once we have the source code, what should be the next step? I think most of you guessed it right. It should be to set up Python. Okay, so again, how do you set up Python? One more thing, you don't have to install Python as well. You can use the actions for Python as well. Actions setup Python. Abhishek, how do you know the name of the action? I've been using GitHub Actions for a long time. So, I know some of the actions names which I use on day-to-day basis. Otherwise, even I would go to the documentation and refer to the name of the action. But which version of Python do you want to install? Okay, you said set up Python, but which version of Python? You will provide that information with the with parameter. So I'll just say with Python hyphen version. Here I will provide the name of the version. Now I will not provide values here, but instead I will use this variable. So I'll just say dollar within the Jinja 2 bracing. I'll just say matrix dot Python. Okay. So this matrix dot Python will refer to the versions that we provided here, matrix dot Python. So this is another automation. Even if you add one more Python version, you don't have to update anything in setup Python. Cool. Now, what is the next step? Once you have Python installed, the next step is to install dependencies. But Abhishek, why are you not installing Python virtual environment here? So this is GitHub provider runner. I'm not going to use it as my personal machine. This runner will be terminated as soon as the GitHub workflow is done, or it will be released from our project as soon as the workflow is completed. So I don't have to install virtual environment. It's just like one-time use virtual machine. That's why. So once the setup of Python is done, I will basically upgrade pip. Okay. So how do you upgrade pip? To upgrade pip, I'll just run Python -m pip install -upgrade pip. Along with that, it is also good practice to upgrade the setup tools as well as wheel. These two are optional, but it is always good to upgrade the pip. But Abhishek, why have you not done this locally upgrading pip? I have already done it on my local machine. Pip is already up to date. So that's why I haven't done this manually while implementing the project. Great. Now let's proceed with installing the project dependencies. So name, if you followed the manual steps, like which we did in the previous lectures, I'm doing the exact same things, but within GitHub workflows. So here, install project dependencies. Okay. How do you install the project dependencies? We will again run the command run Python -m pip install -r requirements.txt. Great. Now, final step, we also have the dependencies. So I'll just say name, train the model. So to train the model, I'll use this command run. I'll basically also list the artifacts once the training is complete. So I'll use pip so that I can provide multiple commands. Python train.py. Actually, this part is enough, but in case there is any issue, I'll just run ls-la artifacts. This is just to ensure once the train.py is executed, model is saved to the artifacts folder. That's the only reason. Now, finally, we will also save the model, right? So anyone who executes this GitHub workflow through their commit or through their pull request, they can just go to a location provided by GitHub and they can download the artifact. That is model.pkl. How do we do that? So for that, we will use a GitHub action. Again, we don't have to write any code for it. We will just use a GitHub action for uploading the artifact. So I'll call the name as upload artifacts and run. We will just use, sorry, not run. we will use action, that is artifacts. Actions upload artifact, not artifacts, but artifact at the rate v4. Okay, so this will upload the artifacts. But once again, which artifacts should it upload? So I will say with name. So I'll provide name for the artifact. Okay, I'll just call it ml hyphen artifacts, followed by, I'll use these two variables. One, I'll use matrix Python just to make sure the artifact names are unique. So I'll use matrix Python followed by name of the GitHub run ID. Sorry, ID of the GitHub run. So this is just to make sure the artifacts location is unique, because we are using Python 3.11, 3.12. Sometimes we might also run on Python 3.13. So it is important to ensure artifact location is unique. Otherwise, your CI file might fail. What is the path where the artifacts are stored? It is stored in the artifacts folder. That's all. So we have the CI file here. Even I want to see if the CI file that I wrote is correct. So I'll just save this file. Pete, I'll call it as implement CI/CD. Now I will go ahead and push this change. Perfect. Now, because I made a commit, this CI should execute automatically because I provided an instruction here on commit, the CI should execute. So if I go back, I should see the CI running. Refresh and CI is running. In case there is any issue, let's go back and try to fix it. Okay, so right now, both of them are running. Train and save the model on 3.11, train and save the model on 3.12. Okay, there is a failure. Let's see what exactly is the problem. So here it says can't open file, hello world mlops, hello world mlops. No such file or directory. Oh, okay. So I provided the name of the file as train.python. Maybe that is because of autocomplete. Let's go back and try to fix it. It's a fairly simple issue. Let's edit this file. And where is the file? Train.python. Let's just call it train.py. Yeah, that should be because of autocomplete. So let's go ahead and save the file. Perfect. So now let's see if the workflow will be successful. Again, details. Okay, so the dependencies are running. Last time it failed with train the model. Okay, this time train the model is successful. Even artifacts are uploaded for 3.11 and even for 3.12, it is successful. Now the beauty is that anyone who wants to, let's say download the artifacts, that is someone who wants to download model.pkl, all that they have to do is they have to expand upload artifacts, scroll down, they will find artifact download URL. So if they just click on it, they have the ML artifacts zip file here. So they can just open it and they have the model.pkl and metrics.json. Within the metrics.json, they can also see the accuracy of the model. So this way, you can help data scientists by setting up Git repository and by setting up CI/CD for their day-to-day practices. Especially in this case, we have implemented something called continuous training process, right? As part of CI/CD, we have automated their training process. So this is how MLOps engineers help data scientists. In this lecture, let's understand the role of ML engineers. In the previous lectures, we learned how data scientists train a model and how MLOps engineers set up continuous training for the models or for the data scientists. If we go back to the previous lecture, we have set up a CI file. Whenever data scientist makes changes to the repo, the CI file is executed. It runs the training process and new version of the model is uploaded to the artifact location. Now you can expect your fellow data scientists or ML engineers to get to this location, download the model.pkl file, maybe for evaluation or testing the model. But what about the end users? Let me take an example. Imagine you are working as a data scientist at Netflix and you have developed a recommendation model. This model is running on your local machine. So MLOps engineer set up the Git repository, set up continuous training process. So every time you make changes, a new version of model.pkl is uploaded to the artifact location. Now your fellow data scientists can download the model and they can evaluate or test the model. But what about the end users? Because you cannot expect the end users to go to the artifact location, download the model and get their movie recommendation. That is impossible. So what you want an API for your model so that the model can be integrated into the backend systems. Something like Netflix mobile application or maybe Netflix website. So users can head to the Netflix mobile application. They can click on the API and they can get their movie recommendations. This is what you actually want to happen. And this is taken care by ML engineers. So this is where ML engineers come into picture. Even in the theory part, we learned that two primary responsibilities of ML engineers. One is to ensure the model is scalable. Because if you're working in companies like Netflix, you might have millions of users. But data scientists, they develop the model locally and their whole purpose is to train the model for efficiency. ML engineer's responsibility is to ensure scalability and performance of the model, typically at the scale. And other responsibility of ML engineers is to develop an API for the model so that it can be integrated into the backend systems. In today's lecture, let's focus on this part. Let's see how ML engineers develop API for the model. Again, just like data scientists, even ML engineers use Python most of the times. I have example here. So I have already developed the app.py. This is exactly what ML engineers do. Few ML engineers prefer Flask. Typically, if the requirement is simple, Flask is a good option because you can develop an API in a couple of minutes. It is also very minimalistic and lightweight. Some ML engineers prefer Fast API these days. We will cover the Fast API part in the future lectures. Now let's try to understand this app.py file. These are just import statements with dependencies. So let's ignore this for a while. These two lines here is basically about providing the path of the model. So the model.path is a variable that is just looking for the model in the artifacts folder, followed by model.pkl as name of the model. And these lines here are verifying if the model exists in the location. If the model does not exist, either ML engineer can return an error or ML engineer can run the train.py to re-trigger the training process and store the model.pkl in the artifacts folder. This is basically for health check. If you ignore it for now, this is the most important part. So this part here is basically developing API for the model, and API is available on the location /predict. So this is the context path for the API. And API accepts the HTTP post request. So if you try to access the API with GET request or PUT request, it will return an error. And most of the models, you use the HTTP post method because you provide the model with input features and model returns the output for you. For example, in this case, we will provide the model with input features like sepal length, sepal width, petal length, and petal width. It will return the type of the flower for us, which is the output. So that's why HTTP method is post. And then now the lines are very straightforward. So this is the definition. This is the decorator. So here the input features are read in the JSON format, request.getJSON, and the features are verified if input features is in expected format. And then here ML engineer runs the model with the input feature, model.predict followed by the features, which are the inputs. And then output is returned again in the JSON format. If there is any error, that is handled using the exception. That's it. These lines are fairly straightforward. Now this line here is actually running the API. So here we have defined the API, but this API is run using app.run followed by host is localhost and port is 5001. In my case, I have something run on 5000. Otherwise, 5000 is usually preferred as the port. Now let's see what happens when we run this app.py. So Python 3.12 followed by app.py. If you run into any dependency issues, just try to download those dependencies, then run Python 3.12 app.py. So you can see here, this says API is running on localhost followed by 5001. Let's take a different tab, and on this tab, let me run the curl command with input features. So curl -x post, this is the command. Curl -x post followed by URL followed by /predict, which is the path to the API. I'll change the port to 5001. Content type is application JSON, and these are the input features. Now let's see what happens when we execute this command. We should see the output target as 0 or 1 or 2. So prediction is 0. That means flower type is Setosa. Let's try to change this. So I'll try to provide 10, 1, maybe 5, 2. The prediction is 1. That means the flower type is versicolor. Again, let me change it to something like 1, 1, 1, 1. It should return Setosa according to the testing data. Perfect. So it returns Setosa. That means model is working absolutely fine, and it is also hosted using an API. So this is how ML engineers set up APIs for the models. In this lecture, let's understand how MLOps engineers can help ML engineers. So if you remember the previous lecture, we learned how ML engineers create an API for the model to integrate model into the backend systems. But still, even after creating API for the models, if you remember, we were running the model on the local host using some Python commands. That means to make the model publicly available, few more steps are needed. And those steps are related to deployment of the model. And this deployment is carried out by MLOps engineers. We learned the same thing in the theory part as well. MLOps engineers deploy the model with all the best practices. It can be containerizing the model so that model runs anywhere and everywhere. Then it can be creating infrastructure for the model, such as virtual machine, Kubernetes cluster, etc. MLOps instance also generate Kubernetes manifest for the model, and finally deploy the model to the Kubernetes cluster using best practices like networking, load balancing, API gateway, security, everything that is required. We will learn about these activities in the future lectures once we understand few MLOps tools. But for now, in this lecture, let's understand how MLOps instance containerize a model. We will take the same example. So I'll go back to my terminal where I have the source code, and I will start with writing Docker file. I already have a Docker file. I'll just remove it and I'll start writing a new one. Perfect. So basically we'll start with using a Python base image from Python colon 3.12 hyphen slim. I can also use Ubuntu or Debian Alpine base image. The only reason for choosing Python base image is that if I go with those images, I have to install Python on top of those images. So to avoid that, I've directly chosen Python 3 base image. I'll also choose a work directory. I'll go with /app. I always prefer copying requirements.txt or dependency file first and executing the dependencies. I do this even before copying the source code so that Docker image size is significantly reduced. Perfect. So I copied the dependency file. Now I'll proceed with upgrading the pip. Right? Run Python -m pip -upgrade. Pip. Perfect. Now run Python -m pip install -r requirements.txt. Great. Okay, now let's copy the source code where we have app.py, train.py, and then we will expose 5001 and finally run cmd within the braces Python, comma, space, app.py. That's all. So this is all what we need to put within the Docker file. Let me quickly explain it one more time. So I'm using Python 3 base image. I'm choosing a work directory. I'm copying the requirements.txt or the dependency file and installing the dependencies. It is always a good practice to do this before copying the source code so that Docker image size is significantly reduced. Then I copied the source files, expose port 5001, and using the CMD, execute Python app.py. Perfect. Let me copy this and run docker build -t hello mlops colon latest followed by the path to the Docker file. Okay, let's see what happens. So it says some issue with Python -m pip install. Oh, okay. I forgot adding install here. So I just said Python -m pip, but I forgot to add install. Okay. I think now this should work fine. Let's see. Great. So now it upgraded the pip and it is also installing dependencies from requirements.txt. Once this is fine, this will run app.py so that we will have our model running within the Docker. So now I'll run the container with the model docker run -d -p I'll bind the port to the local host so that I can access the model on the local host as well. So -p 5001 hello MLOps latest. Great. So now we have the container running in the background. Let's verify. Cool. So we have the container running in the background. So on the other tab, I can just use the curl command and verify on the local host on port 5001, I'm running the model. So with the input features, it confirms the output is Setosa. Cool. So we also learned how to containerize the model. Just to let you know, this is the very first activity using which MLOps engineers help ML engineers. Once the containerization is done, there is a lot to do, such as infrastructure creation, creating Kubernetes manifest, creating Kubernetes cluster, installing the model on top of it. We will learn all of this in the next lectures or in the future lectures of this series. Right now, the intention is to show you how MLOps engineers communicate with ML engineers and help them with day-to-day activities. Awesome. So I hope you got a very good fundamental understanding of how MLOps engineers, data scientists, and ML engineers work together to train a model, save the model, run the model, and also to ship the model. Just remember it this way. MLOps engineers help data scientists with training and saving the model. MLOps engineers help ML engineers with deploying the model. We will learn more about MLOps engineering as we proceed with next lectures of this course. But for now, I hope you got a good fundamental start. In this section, let's focus on data version control and data versioning. This is the very first lecture of this section. So let's understand what is data versioning and why